This is my semester project for COP5611, the Manufacturing Software Test Suite. These are the key terms, but the ones that I want to concentrate on is ESS, ATP, TSS. ESS is environmental stress screening. That's the tests that are performed in parallel in a loop-back fashion. And the ATP tests are done in series, and they're basically just testing that the box was put together correctly. This semester I developed a manufacturing software test suite for testing aircraft spacecraft computers, which will be composed of two large pieces, the TSS and the ETS, running in the UUT. The academic concepts that are being illustrated are system calls setting up shared memory for IPC communications, using IPC message queues for IPC communication, socket programming for communications, forking and executing new processes in attached mode using wait, system call, forking and executing new processes in detached mode, utilizing dynamic memory allocation in order to store results on the heap, linking against dynamically linked libraries, both against a custom library and system libraries. This project is a MSTS that can be demonstrated on SBCs and to custom computer manufacturers which utilizes custom SBCs for their avionics or whatever application. We're also illustration developing an application framework in order to divide work to be assigned to different software engineers to develop each test from start to finish, from the top layer all the way down to the device driver layer. This way you can have scalability, and depending on the amount of money the company is willing to spend, you can either ramp up development or not. So, what are the practical concepts here? Using this framework, we can divide work to ramp up development speed or ramp down depending on how much money the company is willing to spend. The ETSS software was written in a way that can be ported over to embedded environments. The ETSS software utilizes a custom developed web server using sockets, because in embedded environments you most likely cannot download Python and develop a Whiskey server or download Tomcat and basically develop some kind of Java-based application as your web server. Although there are ways to do that in certain cases, especially if your embedded system is a full computer, but we're not going to go into that right now. The important thing is we have scalability. For example, imagine that your custom computer system has 10 custom peripherals, which means you can have 10 parallel software engineers developing each test from start to finish, all the way from the application level to API to device drivers. For example, a system using VxWorks 6.8 RTOS, one of the differences will be how threads processes are used. In VxWorks, threads and processes are one and the same, which are called tasks. However, the socket library is practically the same, and sockets is very much a one-to-one translation, and therefore this framework that I'm demonstrating today can be ported over to a VxWorks environment pretty easily. This is the hardware details where I was developing my software and how I'm going to do this demonstration. So I have a Dell laptop that has Linux installed on it, and I have a Windows computer. Software libraries, obviously I'm using pthreads. As you all probably know, C++11 has threads as part of the language. However, in the backend, they're just pthreads, and they act like pthreads. And in fact, in order to use C++ threads, you have to link against pthreads. I'm using the real-time extensions library as well in order to use the POSIX IPC message queues. In Python, I'm using Flask in order to develop my Whiskey server, and Gunicorn would be the production Whiskey server that I would be using if I wanted to run this in a production level server. But running it just raw via Flask is just fine. And XML HTTP requests in JavaScripts are being utilized to do HTTP client software communication with the server. And several other libraries that don't need to be linked explicitly. Some system APIs that I'm using is for shared memory, IPC for IPC message queues, syswait for waiting on forked and executed processes, and of course, even if I don't wait for them with no hang. So still detach, but keep track of the process and make sure that the process is actually still running. And of course, systypes, net, inet, ARPA, inet, all part of socket programming. Programming languages that are being used here, obviously the very first one is C++, more specifically C++11. My custom utilities library is developed in C, and the shared memory server is developed in C, and the manual utility, the client utility for shared memory, is also developed in C. The Whiskey application is in Python 3 for the back end, and obviously for the front end I'm using JavaScript and HTML. So this is a screenshot of the embedded test software running, and it's running in ESS mode. The tests are actually running, and you can actually see the tests running here. The test IDs you can tell, test ID 3, 2, and 1 in this screenshot capture. And of course, the front end from the test station, you can see the test running here, and you can see the results with it being green, and you can tell the 3 tests that are running over here. If you notice over here, the 7, this is a bit mask, and the way I decide that that 7 means 3 tests is by using the 3 bits in the lower end of the bits in a hex number, and I actually explained that in an earlier video in my channel, how bit masking works. So I'm not going to go into details here. If you don't know how bit masking works, I encourage you to visit my video on it, or any other video that's on the internet. I'm sure there are better ones as well that explain it, but I do explain it. But if you're watching this and you've already watched this far, you probably know already how bit masking works. Okay, perfect. Now let's do a live demo. Okay, launching the test station software. I'm just going to launch it with Flask. I'm not going to bother launching it with Whiskey production server. And then launching the embedded test software. Running the server so we can actually have communication. Now the software is actually running and ready to accept communications. Using any browser, we'll navigate to the test station, and we're using port 8484. going to the ESS software. We want 3 tests. And I'll illustrate that real quick here, just for completion's sake. If you go and put in 3 ones here, you'll see that it's a 7. So that's what that means. And if all we wanted was just the test number 3, if we wanted just test number 3, we would put in a 4, and so on. But again, I explained that in detail in the previous video. Watch that instead. The IP address and the port number to the unit under test. And let's try and move this out of the way a little bit so we can actually see the test running at the same time. Okay, ESS execute. And there we go, the tests are running, and you can actually see them running over here, and us asking for queries. So we're continuously asking for results, and the results are being stored in a thread safe queue that I implemented myself using dynamic memory allocation. So we can actually also illustrate here faults. So let's launch another console window. Let's navigate to the semester project folder. Let's go to the shared memory and go to the client. Let's launch the client and let's sabotage it. There we go. It didn't take the first time because of a race condition. I really wasn't being that careful with it, and I overwrote my own sabotage. But if I time it correctly, it'll kill the server. So basically, I sent a queue to tell the shared memory server to exit itself, and it did. And now the test is failing, and we can tell over here that it's got error code 13. And that's probably a combination of errors. Not probably, it is, because I'm using bitwise ORing to not throw away error code, so you can actually backtrack it and see which errors are being thrown by working backwards and deciding. And by working backwards, you can decode which if statements are being executed inside the test. So we'll go ahead and stop the tests. Now, once we execute the tests again, right, all the tests are stopped. The test will start passing, but the color here will not change back to green. Based on industry standards, we don't want to do that unless the test technician clears the errors on purpose. So even though it's passing now, since there was a failure, it's going to remain a failure. So the test technician would have to do this: stop the tests, clear it, and then execute again. And then it's perfectly fine for it to turn green. Okay. ESS stopping again. And this time, let's also go and visit the ATP side. and this one is pretty straightforward. I don't have as many tests on this one right now, but that's okay because this is not as interesting anyway. And there you go. So this is just testing the utilities library that I have, including my little CAN bus tester, very simple CAN bus tester. And this is just a discrete GPIO state setter. Okay, so what do we see here? The very first thing that I demonstrated was this. And the last thing that I demonstrated was this. This here is, this here is the class diagram design of the ESSOS. Now, this is my class diagram, however, it didn't end up being exactly implemented like this, but it's pretty close. The implementation actually ended up being slightly different than what I have drawn over here. And this is a class diagram of the custom web server. Most of the stuff is done in the parent class and the parent object, and then in the child class that's derived from the parent class is the one that makes the web server act the way it does for the purposes of our application. And the design here is just illustrating how this would look like in a real world scenario where you are actually testing a real unit under test. You would have a test station computer connected to a switch or a router, a unit under test to that same switch or router, digital multimeter, an oscilloscope, or any other devices. And these two devices here use skippy commands to communicate with. And as far as you're concerned, those are just the TCP/IP commands that you send in a specific format to those devices. I can go into more details why they're used the way they are, but that would involve going into the history of GPIB and how that type of parallel port communication works. But nowadays, most of these devices all have an Ethernet port, and you just simply talk to them just like you would with any other computer via sockets. And you can write a simple client socket program to do skippy commands. Okay, so this is a code excerpt of my custom web server. This is where I set up the server, where I bind to the port. In this case, I'm using port 8080, using IPv4. I did not want to use IPv6. It's not something I'm super familiar with when it comes to socket programming. This is the actual server where I actually run inside my loop. And here, this actually can be written a lot simpler, but what I did not want to do, because this on line 44 right here, this is a blocking call, so I didn't want to go into a blocking call unless there's data coming in. And that's why I have this if statement here, and that's why I have line 38 and 39 in order to prevent the server from blocking. This way I can exit the server gracefully and not keep ports open and in use, and then not be able to restart my server again later on. Okay, this is the ESS test template excerpt. I will show the whole thing later on, but this is just basically all software engineers that would be working on this project, for example, would use this as a template, and they would put in their initialization specific code here, and then they would actually put their test code right here where the to-do is, and everything else would stay exactly the same. All tests run exactly the same way. This is the actual implementation of the shared memory test. And this is right here where I'm actually writing. Once you set up your shared memory, it's actually pretty easy to write to. You just simply dereference it and you write to it. Okay, this is my thread safe queue. It's very simple. In queue, I put stuff into the queue, and I have mutexes around it to prevent race conditions, because I have multiple threads. I have one thread putting stuff in and another one taking stuff out. Because remember, the test station is communicating with the server continuously as I'm putting stuff in. Okay, but how is this implemented exactly? Well, it's implemented like a linked list. So this is the excerpt right here. NQ uses this. See? NQ, inserted back, inserted back. And DQ uses remove from front. Remove from front. And this works very similar to my stack video. I will also make a linked list video, but I'm not going to go into detail how linked lists work. But basically the gist is like this. You get a new node, and then if the list is empty, the new pointer, the last pointer, the first pointer are all the same. Otherwise, you increment. And then you make the new pointer the last pointer. That's basically what this means right here. Next pointer, you're incrementing to the next location in your linked list. In dynamic on the heap. And here, you're removing the data, but you're removing it, in this case, from the front. And if the first pointer and the last pointer are equal, that means there's just one element there, and you just zero that out. Obviously, after you assign the first pointer to a temporary pointer, because then you're going to actually delete that pointer to deallocate the memory. If you don't delete the temp pointer, what happens is you have what's called the memory leak, and we don't want that. Okay, well, we're actually out of time, slightly over time actually. So in the actual presentation in class, I would actually have to keep this under 15 minutes, but I don't have to. So for the purposes of this video. So I'm gonna go ahead and go to the next section here and actually show live code. So we already went through this. This is what I was showing earlier. But I did want to show the header file as well. Because what I wanted to show is that what I actually have here is I implemented the light web server, which is what's actually running in this application using inheritance, and I have everything that makes the server work on the parent, but everything that's custom is on the child, including the serve file function, which provides us with, oh, it took us to the wrong file. It took us to the, it actually took us to the parent serve file, but what we wanted was the child serve file, because the child serve file overrides what the parent is, and the parent is the default. And in here, what we have is an if and an else. The if simply provides us with the help screen, and we can actually see that here. This is how in industry typically you have a person that actually works just on test station software, and then you have somebody that works just on embedded software, usually. Not all the time. I actually had the pleasure of doing everything. Especially if the company is smaller, you end up doing everything. And that's probably one of the best case scenarios, because you get to write a lot of code. But what I wanted to show was the help screen. This is how they would know what to send when using this. So right now, the ESS execute button is using this command right here. However, I could use this one instead. This one takes in a test ID number, and there's 3 test IDs that we have in this software. So we could have just used this one. And in fact, I will in the future, as part of future work, add more widgets to this one, more knobs, in order to be able to run tests differently. The reason why I chose the ESS mask, because my function that does that, it goes in through automatically and just launches the tests in a loop, and that way you don't have to call it 3 times in order to launch the 3 tests. And that's why we're doing it that way. And I can actually show that here. Right here, in this loop right here. And I use this function here to get the bits. So starting with bit number 0, 1, and 2. And I actually go through this in detail in my bit masking video. So please watch that one. And the ATP test one is this one. As you can see, this does not have a for loop, because this one just launches the test based on test ID, not on a mask. And therefore, the test station would just have to send 3 commands versus just 1, which is also fine. I really don't care which way it goes. But a good embedded test software engineer, what he would do is he would give options to the test station software engineer to do whatever it's required. More options they have, the better they can tailor the tests for the product and for whatever they need. Because in addition to ESS, you also have qualification testing, and this can be used for qualification testing in combination with the ATP as well at the same time. So you can actually have it, and let's just illustrate that. Why not? So we have the ESS test running, and now we're actually going to launch the ATP test at the same time, and they should just work just fine, as long as they don't conflict with each other. And in my case here, they won't. It's simple enough to where they won't. And there, perfectly fine, legit. This is the full template right here. I wanted to go through this. So the software test engineer that would be developing the individual test would put in any custom member functions here, if there are any. Either initialize the error flag or have a template test object that's related to your test. Any specific initializations goes here, and this is where your actual test goes. And then everything else works exactly the same way. You enter the test exactly the same way, and you exit exactly the same way. And to illustrate that, we'll go back to the shared memory test, and we'll follow it based on the template. No extra member functions here. Perfectly fine. By the way, this is the thread safe queue that we're going to be using. And it's of type ATP log rec, which is this guy right here. Okay, let's go back here. Here at the beginning, either template test object or error flag. We have error flag. Okay? Test specific initializations. Definitely test specific initializations right here. Both setting up my shared memory client and setting up launching the shared memory server via forking and execing right here before I ever enter the while loop. Going back to the template. And the test, your actual test goes right here. My test goes right here, as you can see. All the way down to here. And this is where I actually do the comparison here. Right here. This is where I'm actually using the message queue as well. So I send in data through shared memory, but then I compare it by extracting it by dequeuing the message queue, because the server, the shared memory server, writes, when it gets the data that I'm sending here, that I'm writing to, it takes it and writes it to the message queue. And that's what I'm doing right here, reading that message queue to make sure that what I'm sending, that the server is actually reading, and that's how I make sure that it's actually working. And that's how I was able to inject the failure. By sabotaging the server, the message queue couldn't be read, and the message queue did not match what I was returning from this function here. Did not match what I sent on shared memory. And even though I killed the shared memory server, the memory location was still valid. So I was still able to write to it. Just because the server is dead, that did not invalidate the memory location, because it was already set up. And by the way, this is the utilities library that I'm using here. So I put everything inside the utilities library any utilities that I'm using, that I need. Okay, well, this is getting very long, but I'm gonna finish here. I'm not gonna go through the entire code, because we're already 37 minutes into this video. But I do want to talk a little bit about the queue. Why didn't I use a standard template library? Well, in embedded systems, a lot of times you're not going to have access to the standard template library, and therefore I developed my own. And I decided to develop my thread-safe queue to store my data that I need to send to the test station using a linked list based implementation. And the cleanest way that I thought of doing that was using templates. This way I can use whatever subtype I needed to use per test. So here we go. Well, this concludes this demonstration. Thank you for listening. If you like content like this, please like and subscribe. Otherwise, go to Enigma Climbing.